Hey guys, so I had a couple of you ask about the difference between a TXV and an EEV or an EXV. So I figured I'd make a quick video here to just break down the difference between a TXV and an EEV. Essentially, they both do the same job, they just do it in different ways. So we've talked about TXVs, especially with the video that I just gave you guys yesterday and with the training we just did on Friday. I feel like we've done a pretty good job of covering TXVs, but of course, if you guys have more questions, don't hesitate to ask. That's what we're here for. Uh, but I'll start this by reviewing what the parts of a TXV are, and then we'll go into an EEV and what makes it different, why we would use an EEV over a TXV, and then some basic troubleshooting stuff for EEVs that differ from TXVs. So, a TXV or a TEV is a thermostatic expansion valve. We know that. So, with thermostatic expansion valves, we have a couple different forces acting on our diaphragm and on the power head. So, why is the quality going to shit? Whatever. So, we've got our power head, which is this top part right here. The power head is what does all the work. We talked about that already. We've got three different forces. We have our bulb force, which is the opening force. That's what actually puts pressure on our diaphragm right here, which pushes down on our needle to actually open or close this orifice area to restrict or open up to allow more refrigerant through. That's our first force. That's our opening force. And then we have our spring, which is the main closing force. That's going to be this section right here in the bottom of our valve. That's our spring. And then we have our external equalization tube, our external equalizer, which is our secondary opening force, which would bring in a secondary force of pressure. That's this line right here that feeds refrigerant in and up on the diaphragm to counteract the bulb. So we have our three forces, but it's all mechanical force. So it's all pressure balance. That's a TXV. A TXV is strictly mechanical, no electronic components, and TXVs are slow to react, which is why we don't want to use them in some instances. So with TXVs being mechanical and taking time for changes to take effect, they're slow. It's a slow way for us to control superheat, which is fine for single stage systems or even two-stage systems where we don't have that constant shift or that constant modulation in compressor capacity, in system capacity. So with a TXV, again, slow to react, takes time. It's not an instant change with them. With an EEV, or an electronic expansion valve, they react much faster, which is why we have to use them in some circumstances. It's also why they work best or better in some applications than a slow moving TXV would. Because remember, superheat is what we do, it's what we check to make sure our compressor is safe. Superheat is a measurement of the amount of degrees above boiling our refrigerant is as it leaves the evaporator coil. It's how we make sure we have 100% vapor or gas refrigerant going out of the suction line to our compressor. So it's important that we have a valve that can keep up with the compressor's pump rate or compressor's capacity and respond quick enough to protect our compressor at all times, regardless of how fast our compressor may be pumping, or slow in the terms of an inverter driven system or a modulating system. So when it comes to selecting a TXV or an EEV, you'll find most often that EEVs are found on high efficiency units, especially on inverter driven systems, because inverter driven compressors need a valve that can keep up with their modulation. They don't have time to wait for a TXV to catch up to the compressor's change in speeds. If we wait on a TXV to try and catch up to our compressor as it modulates, most of the time you'll find that the TXV can't keep up and we end up with 0 degrees or less of superheat. And then we end up with liquid refrigerant getting back to our compressor, slugging our compressor with liquid, damaging our compressor, and leading to compressor failure. So that's the main reason why we have EEVs over TXVs. They're just faster and it's better application on inverter driven systems. EEVs with their response time are also much more efficient, but the downside to them is cost because EEVs have a lot more going on. So instead of us having these pressures and this mechanical device here with a spring and a diaphragm fed by a little sensing bulb, we'll jump on over to our example. Instead, we have this setup here. So this is a typical EEV setup. So for a typical EEV setup, you have a number of electronic components here. So we have our controller. Oh, that didn't work. We have our controller or our control board or PCB. You'll hear this referenced as a number of different things across the industry, but the simplest way to think of it is a control board. My brand that I'm most familiar with is Rheem and Train. So I'm going to use Train as the example here because Train has EEVs on almost all of their TAM units. It's extremely common to run across EEVs on TAM units. So in a Train, this board would be called our EVC, Evaporator or Expansion Valve Control, EVC. So our EVC has a number of different components connected to it. We have the cable here, which goes to our stepper motor or our EEV. So this piece of the EEV that has your wire going to it is known as a stepper motor. It is a DC volt stepper motor that receives pulse signals from the control board to drive the needle inside the valve up or down. That up or down action is what controls the orifice in this cavity that actually opens or restricts refrigerant flow into our evaporator coil. So on top of the main wire that connects to our stepper motor, we have a temperature sensor here and a temperature sensor here. For Train, those sensors are going to be called your gas temperature sensor, which is this one. You'll see it referred to as GT. And then your evaporator temperature sensor. You'll see it referred to as ET. So you have evap temp, which monitors the temperature of our coil, and then you have a gas temp sensor, which monitors the temperature of the refrigerant leaving the evaporator coil, which is why it's called gas temp. Because remember, going out of the evaporator coil, we should have a superheated gas refrigerant heading to our compressor. This would be our suction line right here. And not every manufacturer uses this guy. Pressure transducers are not on every single piece of equipment that uses an EEV. Pressure transducers give our control board the pressure value of the evaporator or suction side. Why you would use a pressure transducer is for different operation modes of our system. For example, if you have a inverter-driven compressor, inverter-driven compressors can ramp their compressor RPMs down extremely low, and that reduces the velocity of the refrigerant as it's traveling through our coils. Well, when you slow down the velocity of the refrigerant, you can leave something behind. What you leave behind is oil. So you'll have oil coating the bottom of the coil, just sitting in here. Well, that's a problem. Because remember, our compressor needs to have oil circulating through it to keep all of the scroll plates properly lubricated, so that way you don't get metal on metal contact. So a lot of inverter-driven systems will have a dedicated mode called oil return mode. So if you have an oil return mode, you need to know what suction pressure you're reading, so that way this board can calculate if the velocity of the refrigerant is going to be enough to move the refrigerant oil out of the coil back to our compressor. A lot of times when a system goes into oil return mode, it will shut the fans off and literally just run the compressor by itself just fast enough to be able to pull that oil from our coil back to the compressor sump so that way we can keep everything properly lubricated. It also helps ensure that on the next startup cycle, we don't slug the compressor with a big chug of oil on startup because we can't compress a liquid. Oil is a liquid. We don't want a big gulp of oil hitting the scroll plates as it's trying to pump refrigerant through it because that's going to damage the compressor. A lot of these inverter-driven systems have a dedicated oil return mode that they track based off of runtime on compressor signals. So if the compressor runs for X amount of time at X speed, then that board will calculate, okay, I'm losing this much oil per hour while I'm in this run mode, run speed. It runs that through its algorithms to know a general idea of how much oil is left in our compressor. When that algorithm senses that the oil level is low based on its algorithm, not on a sensor, it's strictly based off of runtime. When that board sees that the runtime and the run speed, as it calculates it, has low oil reserves left in the compressor, it will actually shut down a cooling call and run into its oil return mode to pull the oil back to the compressor so that way it doesn't damage it. Once the oil return mode is complete, it will resume normal operation. Some systems will not stop a cooling call for oil return mode, but Trane does, because Trane values their compressors. I don't know as much information on carrier inverter driven systems. Rheem does not stop their cooling calls. Rheem will run it to complete the call and then immediately go into oil return mode as soon as the call is done. And the old school Rheem thermostats would actually have a display status code for oil return mode if it was running in oil return mode too much. Oil return is a whole different beast. We're not going to talk too much about oil return mode, but just know that this pressure transducer right here is used for dedicated things like oil return mode. It's also used for things like freeze protection. So that way, if the evaporator coil drops below a certain pressure, this board knows that that coil is going to start freezing up. So it'll go into what's known as freeze protection. Sometimes that'll generate a fault code or an error code. Sometimes it will not. Sometimes it just goes into a step down or a throttle back, where it'll actually try to pick up the suction pressure to keep it above freezing in an effort to avoid that freeze up. It'll do that sometimes in applications where there's low heat load, like on a mild day, or if it's starting to see an airflow restriction, like if your filter's getting clogged. But those are the primary applications you'll see a pressure transducer. Most of the time, that is on your top of the line equipment, like your Carrier Infinities, your Trane Platinums, your Rheem EcoNets. They all use pressure transducers because they have those dedicated modes to help protect the coil from freezing up and to help protect the compressor from losing all of its oil. The temperature sensors, however, are important to make note of because these temperature sensors fail so much. Most of the time when you have an issue with an EEV, it's because your temperature sensors have stopped reading properly. Temperature sensors can be checked just like any other type of sensor or thermistor by checking the resistance based upon a known temperature. They all have thermistor charts or ohm charts. They're going to be in their respective service manuals. For example, if you're working on a TAM unit, if you go on Google, go to the friendly interwebs and just type in TAM 7 service facts. The first thing that comes up should be a PDF of the TAM service facts manual. If you go into the manual and you scroll all the way towards the back of it, you'll see a thermistor chart for the ET and the GT. They're actually different thermistor charts. They're separate thermistors. I don't remember off the top of my head, but one of these is a PTC, the other one is an NTC. What those terms mean: positive temperature coefficient, negative temperature coefficient. So a positive temperature coefficient means as temperature goes up, so does resistance, or your ohms. That is a PTC, positive temperature coefficient. Temperature and ohms share a direct relationship. One goes up, the other goes up. An NTC, or a negative temperature coefficient, means as temperature goes up, resistance goes down. So your ohms will go down. I don't remember which one is a PTC, which one is an NTC. You guys can go on the service facts and check that stuff out if you want. Like I said, if you hop on Google and just type in TAM7 service facts, should be the first thing that comes up. It's a PDF file. Has a lot of good information. If you want to get good at working on these train units, these TAM units, you're going to live in that service facts manual, because that's what I did for my first year, pretty much my first year straight working on these units. And that's why I know so much about them. That's why I'm so proficient in troubleshooting them, because all of the information that you guys need to work on these units is in the service facts. Going down a rabbit hole, though, getting off topic here. EEVs. So we're going to circle back around here. So the temperature sensors are what fail most often on these guys. So majority of the time, if you're having an issue where you're suspecting the valve is not doing its job, you'll want to start with the temperature sensors. Start by checking the resistance on them. Start by ohming them out, seeing what you're getting based on the temperature that you've got of the lines. Or if you unclip them from the lines, just let them hang in the return air. See where your resistance is. There's a variance that's acceptable. It's usually plus or minus 3 degrees. That's acceptable. Anything outside of that plus or minus 3 degree range considered failed. When you are checking the resistance of the sensors, you're also going to want to check them to ground. The sensors should not have any continuity to ground. If the sensors have a continuity to ground, that means the sensor is shorted, probably somewhere in the wire run. It does happen, and at that point, you're going to need to replace the sensors. The sensors are on a shared Molex connector that plugs into the board, kind of like it shows right here. So if one's bad, you got to replace them both. It is what it is. Always try to put them back in the same place you get them from, and always make sure they're wrapped in insulation, foam tape. Make sure they're properly secured to the pipes. Treat them just like a sensing bulb for a TXV, because essentially that's what they're doing. They're acting as the sensing bulb for the TXV, just using thermistors and electrical signals instead of us relying on a mechanical connection. Now, the second most frequent issue you'll find is going to be the stepper motor. These stepper motors do fail quite a bit as well. They're usually just tiny little DC volt stepper motors. There's not much to them as far as what they're made of. Some quick service checks to do on these guys, and also a good idea for maintenances, is if this stepper motor cannot make good contact with the spindle that it's mounted on, with the post that sticks up that you slide it down onto, then it's not going to be able to properly actuate the needle that sits in here. And since we're talking about the parts of this, we'll go ahead and pull up the next diagram. So this diagram here is a view of what's inside the stepper motor. So inside your stepper motor, there's a couple of big parts to pay attention to. Your power head is what the entire assembly here is called. That's our stepper motor. So in your power head, you guys will notice that you have electromagnetic coils right here and right here. They surround the needle. So the needle is inside the actual valve body, and that is what gets brazed onto the liquid line and the coil inlet. So the valve body and the stepper motor are two completely different pieces of this valve. So when you say you have a failed EEV, you have to specify if it's the stepper motor or the power head, or if it's the actual valve body. Because a failed valve body and a stepper motor are two completely different repairs. I can tell you, for the 7 years that I've been working on train TAM units, I have had to replace one valve body, and I have replaced countless power heads. I can't even count how many that I've replaced. It's been that frequent. The majority of the time, you are not going to have an issue with the valve body of an EEV unless you have trash in the system. If there's carbon buildup in the system because somebody didn't braze with nitrogen, and it makes its way in here and stops up this section right here, well, then unfortunately you're going to have to replace the valve body. And I will tell you from my experience with train units, it's a pain in the ass process to get a torch in there, try to replace that guy. So hopefully you never have to deal with that. Now, the stepper motor is a whole different thing. So with the stepper motor, there's a couple of different checks you can do. The first one is really easy. Just turn the unit off, turn the unit back on again, and listen. A functioning stepper motor will drive itself closed and then drive itself completely open on startup. This is the board verifying the position of the needle on startup, so that way it has a reference point to go off of when it starts to adjust the valve, open or closed more based on the demand of the system. That way it can get that superheat number in the range it's shooting for. And if you guys remember from the previous video, the range most units are shooting for is 7 to 14 degrees of superheat at the evaporator outlet. So, with these stepper motors, the first test is literally just turn it off, turn it on again, and listen. On startup, you will hear a ticking noise. It sounds like this. Tick, 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 tick. That is a normally functioning EEV. It's driving itself closed, driving itself back open, and making sure it has a reference point for when it needs to start adjusting that valve. The majority of the systems out there that utilize an EEV will do this. So when you first power it on and you hear that noise, that's a good noise to hear. That means the EEV is working. Hopefully. It means it's trying to work at least. The second test for these stepper motors is a resistance check. So the EEVs across the industry come in either 5-wire or 6-wire variants. So with a 5-wire variant, you will only have one common. So just like any other low voltage circuit, because that's what this stepper motor is, it's a low voltage DC circuit in most applications, usually about 12 volts DC, you will only have one common wire on 5-wire. The color is going to vary. Sometimes it's gray, sometimes it's blue. You have to refer to your manufacturer literature to determine what the common wire color is going to be. You could also just start checking the wires to each other and see where you get your reading at, because only one of those wires will have continuity to the rest of them. That's your common wire. Pretty easy to figure that out just by trial and error. The 6 wires have 2 common wires. So for the trains, most of the train units and the TAM air handlers will use the 6-wire variant. With trains, brown and red are your common wires, which is backwards for what you normally think, because normally we don't associate red with common, but those are the colors of trains' stepper motor. I don't remember the major manufacturers of these stepper motors. It's the same manufacturers for all the brands. One of them, I believe, is Yaskawa, and I believe the other big one is Hoshizaki. Don't quote me on that, but those are the names that stick in my head when I think about these. So probably close to the money. It's all the Japanese companies. Go figure. So with the 6-wire, you got 2 common wires. And if you notice, the valve that's pictured, the electromagnetic coils, you got 4 of them. This is standard for most EEVs. You'll have usually 4 magnetic coils inside the valve body. They're not oriented in this way. They're oriented around the poles of the circular stepper motor. So for example, if you've got a circular stepper motor like this, instead of it being like this, it would be just like you'd see on a regular shaded pole motor. So on a regular motor, your stator is going to be in place, and your rotor is going to be what gets moved by the magnetic coils, and it'll be moved by the magnetic coils because it'll have these poles around the motor that become electromagnetically charged with a positive or negative charge when they get voltage applied to them. That makes the magnetic field that actually creates motion of the motor itself. So, kind of like this has a dry stator and a wet rotor. Same thing. It's just a motor. You have a stator and a rotor. The rotor does the spinning. The stator is the piece that stays in place that the rotor is actually moved by. So the stator is what has the magnetic charges in it, the magnetic coils. The rotor is what actually spins the needle down into the valve. So when you get a call to either open or close the needle of an EEV, you get positive and negative charges around the poles. And this creates a magnetic field which will drive that needle one direction or the other, depending on how it sends the voltage down our wire to power these magnetic coils. Now, you'll always have about 4 coils in the motor, which is why you'll always have 4 power wires to check to common. With the 5 wires, like the 5-wire stepper motors, all 4 of these will share a common, so they'll all meet at one point, usually at the base of our stepper motor, where they go back to the board on our common. Now, on 6-wire, you will have usually the top and bottom coils will share a common, and the left and right coils will share a common. So in that instance, you would have, for example, here and here would share a common, and then here and here would share a common. That's why you check them to each common. So I mentioned the 6 wires that Train uses. They have brown and red as your commons. That's an R, I swear. So you have brown and red as your commons, and you have certain colored wires or certain coils you need to check to each common. Brown always gets tested to blue and yellow for Train. So you check the resistance or your ohms of blue to brown and yellow to brown, and red always goes to orange and white for the 6-wire EEVs. So you would go red to orange, red to white. Train expects to see 46 ohms, plus or minus 3, on each coil. So you would expect to see 46 ohms from brown to blue, from brown to yellow, from red to orange, and from red to white. If you see any drastic variance, that usually means a coil has failed. If you lose a coil and it's no longer in the circuit anymore, and this no longer has any electrical charge, it's just dead, it's not doing anything, your needle will spin here to here to here, and once it hits this, it just stops. When it hits that point, it's not going to do anything because there's a dead spot right here. There's no charge, positive or negative, to move that little rotor past this point. So once you lose a pole, that stepper motor is dead in the water. Can't really do much. It can move in this little section. That's it. But once it hits this area, it's not going to open or close. It's not going to do anything. So once you lose a coil, that's it. Stepper motor's done. So most EEVs expect a 40 to 50 ohm reading. Doesn't matter brand. It should be 40 to 50 ohms for most stepper motors out there. Doesn't matter if it's Train, doesn't matter if it's Carrier, doesn't matter if it's Daikin. They want to see 40 to 50. That's a normally operating stepper motor. All right, so now we've covered the electrical troubleshooting on this stuff. And same thing as the sensors. With the sensors, I'm just going to go ahead and erase this stuff instead of going back through all of it. So same thing as when we're thinking about testing the sensors resistance. When you're testing the resistance of the stepper motor, you should not get any continuity to ground on any of this stuff you're testing. And remember, resistance checks have to be done with the plug removed from the board. So the Molex connector has to be off of your board to do a proper resistance test, because you want to isolate the stepper motor and only see what the coils are giving you for resistance. You don't want any backfeed from our board, which you will get if you try to test it plugged in. On top of the resistance checks, there are DC volt checks you can do as well if you want to test it while it's running and while it's powered. Those are a little trickier, and the DC voltages vary from manufacturer to manufacturer. To be honest, I've never bothered with the DC volt checks on Train's stepper motors because the resistance checks are pretty foolproof. The majority of the time you have an issue with these stepper motors, it's going to be a failed coil. Again, most of the time, the valve body isn't going to have an issue with it. If it will have an issue with it, you can usually tell that by taking a temperature difference from the inlet of the stepper motor, so the liquid line going into the valve body, to the outlet or to the inlet of the coil. So from stepper motor inlet to evaporator coil inlet, you would take a temperature reading from here to here with this valve in full open position, and that would tell you if it's actually restricted. Because if it's not allowing proper refrigerant flow or your pressure doesn't come up when the valve opens, that's another indicator that it's blocked up. So you would see a severe temperature drop from here to here if it's stuck shut or restricted. You would also see that our suction pressure never actually goes up, even though the valve may be reading open. Trane also has a series of pins on their board where you can actually do, it's 3 pins that stick off the board. One will say open. That is an O, I swear. One will say close, and the other one will say common or test. It actually says test, not common. So it'll say test. So these 3 pins are how you can actually force your EEV to drive open or closed. So if you short the open to test pin, that's going to be doing an open test where it will drive your stepper motor full open and keep it in that position for about 5 minutes. After that 5-minute timer, it will drive it full closed, then resume normal operation. A close test, same thing. You short the test to close pin for about, I think you only have to short it for about 10 seconds. But when you short those pins together, it'll drive the valve full closed and keep it full closed until either the low pressure switch trips or 5 minutes, whichever comes first. So those are some ways you can test the valve to make sure the stepper motor is driving open or closed the way it's supposed to. When you do the open or close test is when you can check the DC voltage on the Molex. Again, the service facts tell you what the DC voltage is supposed to be. I do not have that information memorized like I do the resistance readings of a stepper motor. Okay, so we've talked about resistance readings, what they're supposed to be. We've talked about how the EEV works, how to test for a restricted valve body, how to do the open-close test, the evap temp sensor, the gas temp sensor, what a pressure transducer is and how it works, what applications you would expect to see it in. I think for the most part, that about wraps up EEVs. So, I mean, they're a little bit different. They're not quite as simplistic as a TXV is, but again, it does the same job. They both regulate superheat. That's their main primary functions, is to regulate superheat at the outlet of the evaporator coil. It's just there to make sure that our coil's doing what it's supposed to and removing the amount of heat it's supposed to. And then they're there to make sure we have enough superheat to keep our compressor protected outside. You would use an EEV over a TXV in high efficiency systems because they're faster to respond. You would also use it in applications where you have an inverter-driven compressor because our compressor modulates and makes changes on the fly very quickly. We need a valve that can keep up with that, and a TXV is just too slow to respond. So it can't keep up with the compressor's modulation. And if we try to run a TXV on an inverter-drive compressor, most of the time it's just going to lead to a dead compressor. All right, so I think that about wraps up EEVs. Again, if you guys have any questions or you want to dig into this stuff further, of course, you're always welcome to talk to me about it. Ask me some questions. Give me some scenarios. I'll be happy to go through them with you. But otherwise, this is the difference between a TXV and an EEV or an EXV. They are the same thing. The TXV is just a slower variant of the EEV. But it is important to understand these EEVs. They're becoming more and more popular as the push for efficiency becomes the forefront of our industry. And it is becoming increasingly common, especially with the rise of ductless and side discharge units. All right, guys, that's all I got for today. Thanks for listening. Hope you guys learned something. If you guys have any questions, let me know. And I will see you guys tomorrow for a wonderful day of fun at work. Muffin Man signing off.